Thanks everyone for coming. It's I know that you're all busy with deadlines and papers and other things, so it's an honor to have you all here to listen to my talk. And I'll be sharing our recent work, which is a very different flavor. It's not traditional wireless, but it's more of along the line of building mobile systems, wearable systems, and wireless system toward healthcare. And I graduated from here 3.5 years ago with my background in computer science plus mobile systems. So I thought, let's give it a try to apply what I've learned here toward medical and mobile and healthcare. So the topic that I'll be talking about today is different techniques and new techniques for non-invasive sleep quality monitoring. Sleep deprivations, whether you know it or not, right? It's 35% of Americans have sleep deprivations. So look to your right or look to your left, you probably find the one that is sleep deprived right now, right? And I guess with the PhD students, it's even the rate would be higher. And we know that until we see the consequence of sleep deprivation, we don't really try to treat it. But it actually correlated with many clinical diseases, going from depression to diabetes, obesity, heart failure. So over the short term, and especially when you're young, it's not a big problem. But as you get older, it becomes serious problems, and it even more so with kids, right? So these are the few pictures that I just used to illustrate the fact that kids are affected even much more heavily compared to adult, because the effect of sleep deprivation would be carried for their whole life, right? And the bad news is that 1 every 9 kids have this problem, has a sleep deprivation problem, and it linked to sleep excessive sleepiness, obesity, allergy, among many other problems. And because of the seriousness of these and of the consequence, the American Academy of Pediatrics call for screening, for early screening and of testing children with sleep problems. Yes?
I thought that obesity was the cause of some of the sleep deprivation rather than the way around. You're saying sleep deprivation can cause obesity?
That's right. Yes. So it's both ways, right? And so for screening, for studying sleep quality, the way that doctors are doing now is relying on a gold standard device. A gold standard device is a device called polysomnogram, or PSG. And what I'm showing here is a polysomnogram with many sensors that are attached to a person's body. And in this case, normally it would have around from 20 to 30 something sensors that attach on the person's body, and it group into many different groups. But there's a number of sensors. For example, a chest belt here that can be used to monitor the breathing volume of a person, and or monitor the breathing activity, that mouth, the nasal cannula that attach to the nose of a person. It also, there's a number of sensors that are attached on the person's head, such as a brain sensor, chin sensors, and eye sensor that are used to monitor your brain signal, your eye signal, and your muscle signals. And this is an actual footage that I took 3 years ago in a hospital, in Children's Hospital in Colorado, where this kid doesn't look very happy because she was connected all the device, all the sensors onto her head and then walk around, and the doctor would ask her to sleep normally. Give it a try and you will see how hard it is, right? Especially because when we sleep, we are unconsciously trying to take things that are making us uncomfortable. So because of that, doctor need to wrap them around. Otherwise, during the sleep, they will just take those sensors out, right? And this setting is not only uncomfortable, but also require extensive setup, which would range anywhere from 45 to 1 hour of setup that a nurse would need to spend on the person to set it up. And then after the study, the doctor would need to sit down and read the output of these sensors. So it's because of all this sophistication, it costs a lot. A sleep study costs anywhere from $3,000 to $5,000 per night. $3,000 to $5,000 per night. And the device itself costs anywhere from $40,000 to $60,000 per device, right? So it's very expensive. And another footage that I have here, unfortunately the sound doesn't work, is that a kid was waken up during the night while wearing these sensors, right? And what he was saying is that my face feel like really smoother. His face was stacked with all the equipments, all the sensors, and during sleep he tried to take those sensors out. And because of that, the sensor become very erroneous, it's uncomfortable, and we asked the question of, can we build a better system? Can we establish a new gold standard that can be used for not only making the system much more unobtrusive, simple to use, yet accurate and cheap, right? So that's the mission that we take 3 years ago when I start my positions in University of Colorado, Denver. So today I'm going to be talking about two systems that are going toward that vision. One is the use of wireless technologies to build a system that can sense your breathing volume while you're asleep. And the second is a system that can sense your brain signal, your eye signal, and your muscle signal from inside the ear. So the first system is, we name it WiSpiro, as opposed to normally it will be a traditional way of measuring your breathing volume is use the spirometer, right? So, but we want to build a wireless system that can sense your breathing volume. So the goal here is we try to remove these sensors to make it more unobtrusive. So how do we do that, right? So there are existing technology that have tried to do this. For example, you can use a depth camera, and a person will sit in front of a camera, and then the system will try to reconstruct the surface of your chest, and from that you estimate the chest movement from which you can infer breathing volume. And another system could be using the same mechanism but use laser. The problem with this is it requires direct line of sight between the camera and the chest of a person. And it also, the problem with this is that it doesn't work during sleep. Why? During sleep, your body moves all the time. Well, often your body moves. Not only that, your body is covered by blanket or cloth. And because of the coverage of your blanket or cloth, the camera doesn't have access to your chest movement, and that's why the estimation normally not accurate anymore. There's a second technique that have been shown in the literature is using wireless signal. The very nice property of wireless signal is that it can penetrate through your cloth very well, and that it can bounce back, from which hopefully you can infer some breathing activity. Existing work can only estimate breathing rate as opposed to breathing volume. And next I will be showing a number of challenges in order to estimate breathing volume for a continuous, for a long duration, such as the whole night sleep, at a very, very fine grain. So what we propose is a WiSpiro, a system that would follow and monitor a person as the person sleeps. And the high level idea here is that we try to capture the Doppler effect, or the phase changes caused by the chest movement. So the principle here is that when you send out a wireless signal, when it bounces off the chest of a person, the phase of the signal would change as the chest of a person is moving. Right? So the correlation between the phase and the distance changes will be reflected in the phase of the received signal. And what we capture is a phase change. And what we need to do is we need to infer the distance of how much that the chest has moved. And then from the chest movement, we would want to infer the breathing volume. So that's a high-level idea, right? So this is a correlation between the distance and the phase changes. And as you can see, when the chest moves back and forth, the reflected signal would be shifting in phase, right? Now, the fundamental physics is not so hard. And of course, this is known in the literature. But in order to make this system work for the whole night sleep and fine-grained breathing volume monitoring, it is very challenging. The first challenge comes from the fact that humans change their posture during sleep, and it has inherent consequence on the signal domain. And what we see is in this small screen here showing the reflected signal when the radar is beaming to the chest of a person. But when a person moves, because of the direction of the signal, and now the signal is bounced off to another direction, it no longer reflects the phase changes as well as what it normally would reflect. And because of that, now you see all the breathing pattern is gone, right? So this means that our system must be able to estimate patient posture and then navigate itself as the person sleeps, right? So the second problem is coming from the fact that the human body is very different from a cylinder. And what does that mean? It means that, so with a cylinder, given the same amount of volume, the chest or the surface would move the same at any given point. But on a human's body, it's not the case. For example, if you measure the chest movement from 2 points on the chest, it would, one is from the xiphoid and the other, let's say, from the heart area, it moves really different, right? The reason for that is that the movement on the chest of a person is regulated by different groups of muscle. And these different group of muscle cause different movement on a different point on the chest. And what that meant with our system is that our system must be able to know where it is pointing to at any given time. And by knowing where it's pointing to, it would use the corresponding inference function, which map between the chest movement to breathing volume, right? And the third challenge is coming from the fact that individual chests are very different from one to another, right? And a kid would have very different breathing patterns and a very different correlation between breathing volume and the chest movement. And so what this means is that our system must be personalized for different patients, right? And last but not least is occlusion. Because as you sleep, what could happen is you might block the line of sight, the direction between the transmitter and the receiver and the chest, right? So the system must be able to detect and avoid those obstacles. So what we propose is a 3-component system that has a one-time trainer that do a lot of training for understanding where the system is pointing to at any given time. Not only that, it also tries to learn the relationship between the chest movement and the amount of air that is coming in and out on the chest on the person. And then the volume estimator would use the output of these to decide whether a body movement happened, or if not, whether the chest movement is sufficiently clear for us to make an inference about the breathing volume. And the last component is the most important piece, where it would control the radar. It would move around the bed as you sleep. And it would track where you are to know what is the correct correlation function that it should use. So at a very high level, so the volume estimator must be able to tell whether there's small movement. For example, during sleep, you might move your leg, you might move your limbs. So that should be ignored. But when a large body movement happens, the system first needs to detect that there's a body movement, and then it will need to trigger the radar navigator to move the antennas, right? So on the radar navigator, there's 2 key components. The first piece is we try to teach the system about where it is looking at any given time, so that it will know which correlation function that it should use. So the idea is that if we divide the chest of a person into different segments, then the question here is, can we really tell where the system is looking at? By looking at different signal patterns when it reflects back, we can actually tell very clearly whether the system is looking at the heart, or looking at the abdominal, or looking at the right side of your chest. The reason is, as I mentioned earlier, different muscle group on your body would regulate the movement, and different muscle group actually move differently. So if we look at frequency domain, time domain, and we combine them together, it reveals very unique patterns. This is just a quick example of just one feature. We use MFCC features on 9 different points on the chest of a person. And as you can see, it's relatively distinguishable. And when we combine with other features, it becomes really, really clear where we are looking at any given time. Now with the posture detector, we derive an algorithm that we have a scanning algorithm that allows us to know what is the posture of a person. And it is crucial for our system because we need to know what's the angle that the person is making with the surface of the bed, so that we know where to navigate our radar to. For example, so the way that the system works is our radar would scan through, and after it scans through, based on the vital signal that we see on the surface of the bed, we know the distance on top, and then from that we can calculate the angle. And once we know the angle, we can know where to move the antenna to. And that is the first part of the localization that we need to do on that the antenna need to do. And after that, it would do fine-grained localization to know what the area that it needs to look into. So when we put the system together, this video shows how it's actually worked in real life, right? So we have a person, when the person, and this video is speed up, so don't worry when you see the person breathing very fast. So when the body movement happens, first is the system will detect that, there's a body movement, and then it will start scanning. And keep in mind that all of these processes are done autonomously and for whole night sleep study, right? So it will first scan around to see what is the angle that the person is making with the bed surface. And in this case, it will know that, okay, the angle is like this, making with the bed surface like this, so it needs to move back here. Once it go back to the, once it has an orthogonal direction from the antenna to the chest, it would do the second step of localization, which is knowing where it is pointing to. And most of the time we try to monitor the heart area. And so this is another example where when the body moves, the antenna move again. But pay attention to the antenna here. The first step is it would try to find what direction that it should point to, but then it will make a minor adjustment as well. And that minor adjustment is to know, to point to the area that of interest. And in this case, it's a heart area, right? So by doing that, the system can autonomously change its own position, point to the point that it needs to point to monitor the breathing volume. And so that it can use the correct mapping function between chest movement and breathing volume. So we did an experiment with 6 subjects for 30 hours of sleep, and we want to see how well do we do in terms of estimating breathing volume, right? So these figures show an estimation of our system compared to a ground truth, which is an FDA-approved spirometer that is attached to the mouth of a person during sleep. And these curves show how well we do. So the red curve show the ground truth, and the blue curve show the estimation that we can do for the whole night's sleep. And as you can see, the accuracy is relatively high, and the error is only 0.02 little. Now, what does that mean from the clinical domain? That's a more important question that we wanted to ask, right? And how can doctor use this information to make diagnosis? So that leads to our next experiment, where we pick 3 patients, or 3 subjects. One doesn't have any breathing problem, another have some snoring problem, and another person have a mild hypopnea problem. So hypopnea is a problem where your breathing volumes keep reducing during sleep. And this is caused by one of the 2 reasons. One is your chest movement is getting less and weaker and weaker during sleep, or it's caused by your brain stop controlling your muscles during sleep. In either case, what should be shown in the breathing volume is that you see the gradual volume changes, and it keeps dropping. And at some point, when you don't have enough oxygen, your body would wake yourself up so that you would regulate your breathing, and from that you would get enough oxygen. Otherwise, you die, right? So because of that, detecting mild hypopnea is very important. So in this experiment, we have 3 subjects to perform our experiment, and then we get the results, and we remove the identity and also removing the known clinical problem of those subjects, and then we give it to doctors for them to make diagnosis. So based on this result, they can actually tell who has what problem. So for example, the doctor was able to say that, so this person was snoring because during snoring, your breathing volume tends to stay flat and it vibrates. And it's called flat top cycles. So during mild hypopnea, your breathing volume is supposed to be reducing, and if you look at the longer trajectory, it's actually reducing significantly over time. Right? So those are the signatures that the doctor can see and can make diagnosis on that. So with this system, we can remove these wires, we can remove the breathing volume sensors. But the next question is, how about the sensors on the head of a person, right? Because those are also the source for the distraction and for uncomfortness during sleep study. So we asked the question of, can we remove all of these wires at a lower cost? So then the first step that we try to do is, we want to understand, why does the doctor need to understand about the brain signal, the eye signal, and the muscle signal, right? So a little bit background about sleep study or sleep quality monitoring. So normal human sleep is divided into 5 different stages. Of course, awake is one, and when you start going to sleep, your body would a little bit more relaxed, and then you're still aware of the surrounding environment, but you're actually in a sleep state 1. That is when so when you're awake, the brain signal is of the frequency from 8 to 13 hertz. And as you drift into sleeping, the brain signal starts slowing down, but you're still aware of the surrounding environment. That's what the state 1 is. Now in the second state, which is counterintuitively, your brain signal is actually going up, right? So by looking at the brain signal and the frequency of the signal, it actually go up. And not only that, the signal are following a certain patterns. For example, it follows spindles, which is saw-like signals, or it also exhibits some of the K-shaped signals. So if the signal go up, down in the K-shape, and then it repeats the pattern itself. So what that means is that we need to have access to the brain signal in order to tell what state of a person that the person is at any given time. But not only that, not only the brain signal. During delta sleep, which is sleep state number 3, the brain wave now significantly slowed down, but we also need to look at the muscle signal, because at that time your muscle is really relaxed. But the most important state during sleep is actually REM, which is stand for rapid eye movement. So with rapid eye movement, your brain signal have a mixed frequency. So if you just look at the brain signal itself, it's not enough for us to classify whether you're at a REM or not. So, but doctors look at the muscle signal and the eye signal. So REM, as the name stands for, right? It is during that state, which is the deepest sleep stage, that your eyes move really fast. Your eyes move at a frequency that are abnormal, right? So that's why doctors need to see the eye signal in order to make diagnosis whether you are in the REM sleep or not. And also, not only that, during that stage, the muscle signal is much more relaxed, which can be shown in the if we can capture the muscle signals. Now, all that mean that we need those 3 signals in order to do sleep quality sleep qualification well, right? So that leads to our next piece of work that is called a lightweight in-ear bioelectrical sensing systems. So the idea is that existing work have been tried to quantify your sleep quality. For example, you can easily download app on Android or Apple Store for monitoring your sleep quality. By just downloading the app on the phone and then placing the phone next to your bed, it actually can monitor how well you sleep. And of course, that is pseudo sleep quality monitoring, because it doesn't have access to your brain signal. It doesn't have access to your eye signal and muscle signal. All it does is that it based on the sounds that you would make when you're sleeping. When you move on the bed during sleep, the friction of your body and your limbs caused with the bed would make noise, and that noise would be captured by the phone, and then those applications try to make use of those signals. The great thing is that you don't require any wearable device on the person. The bad thing is that it's absolutely not accurate, right? So because of that problems, there are systems that try to build wearable devices that capture the signal that we wanted to capture. For example, out of all the devices that we see on the market, Zio is a great example of a device that tries to capture your brain signal. Now, they try to infer your sleep quality by having a headband, and imagine you wear a headband on your head and you go sleep. There's 2 options for you to pick with this device. One, you need to tie it really tight and go sleep so that it doesn't fall off. And if you do that, you either try to take it out when you're sleeping because it's uncomfortable, or it will fall out if you don't tie it very tight, right? Because of that, the accuracy of this device is really low. Even though it is a commercial device, the accuracy is around 40 to 50%. And because of the low accuracy, people start buying at the beginning, and then they stop buying, and the company go bankruptcy, right? So the company filed bankruptcy in 2012, and we were able to still get the device from eBay to compare with our device. But in any case, this is very uncomfortable, inconvenient. It can only capture one signal out of the all signal that we want. So we asked the question of, can we provide all of the 3 signals at a much lower cost and at a that is more comfortable? So that's led to our recent work called lightweight, inexpensive in-ear bioelectrical sensing signal, or stand for LIBS, right? So the idea is that we of course want to capture those 3 signals. So the first question is, how do we capture that signal and yet still make the patient feel comfortable? right? And then we thought about where's a good position to put this kind of sensors. And what we found is that inside the ear is actually a better position to do this. Why is that? Because it's close to the 3 signal source of interest. And it also inside your head so that it has much less chance to fall off during sleep. Unlike anything else that you mount on the surface or on the head of a person, right? But it is extremely challenging. So the first challenge we run into is that from signal processing and literature, what we know is that in order to capture in order to capture 3 signals, you need to have at least 3 or more number of channels, right? So that you can split the signal out. But in contrast to that, in our case, we only have 1 single channel, which is inside your ear. And we try to extract the 3 signal out. So that is a fundamental limitation of existing literature when we start this work, right? But we're not stopped there because these 3 signals are overlapping in frequency and amplitude. And not only that, even more challenging because even with the same person, the signal varies, let alone from different persons, right? So it's very hard for us to split the signal out given the single signal source. So what we do is we derive a new signal splitting algorithm that is a combination of non-negative metric factorization with support vector machine and using machine learning. So the high-level idea here is that if we can represent a signal as a linear combination of different 3 signals and a noise, then it can be, and if we can represent that or defactorize or factorize the signal in 2 terms. One is the spatial temporal metric that represent the core of the signal, the part of the signal that doesn't change very much, which is metric W in this case. And another metric, which is activation metric, is showing the signal, the changes of the signal over time, and the weight of each component on the composed signals. So by doing that, by factorizing the signal, we reformulate this into an optimization algorithm where we try to minimize the distance between the product of W and H to X, right? So the problem now becomes finding a combination of W and H so that the distance between the 2 are minimums. And one of the questions that we need to solve here is that what is the right distance metric here? Because for us to pick to have the right distance metric, the distance metric must be insensitive to the scale of the signal. This is a problem caused by the way that we design our electrodes. The way we design it is that when it goes inside your ear, you don't know whether it's go really deep or it's go not so deep. And if it goes really deep inside your ear and it makes very good contact, then it can maintain very good high quality signal. But on the other hand, if it doesn't go very deep, then the signal is still having the same shape, but the scale is much lower, right? So what that means is that this metric must be invariant regardless of the scale of the signals, right? And then after that, we applied multiplicative updating iterative rules to optimize and iterate through multiple times to find the right combination of W and H. Now, the hard part here is we need to be able to find W, because if we don't know W, neither H, then it will be then the iteration will not converge, right? Yes.
Okay. My question is, do you really have to separate them before you can just classify them into 5 stages?
Good question. So I'll cover that. But the short answer is by separating them, you improve the classification result. But when we develop this, one of the goals is using this for sleep study. But the potential for this is much larger than just sleep study, and we will have a much wider class of application that an in-ear sensors can do. So I'll touch on that. But so what we've talked about so far is that if we know W, of course we know X from the measurement. But if we know W, we can estimate H, right? But how do we get W? So the way that we estimate W is based on a single class support vector machines with an idea that we need to separate the hyperplane P to separate all the data point from the origin with the maximum margin. And by doing that, we can estimate doubling. So in summarize, right, the key algorithm here is that we use a short phase of training, and then we combine that with a factorization algorithm, and from that we can estimate, we can get out the 3 signal on live. Now, once we build this, so that is the signal separation problem, and that's how we solve it, by proposing a new algorithm. Now, the next part is the design challenge, right? As I mentioned earlier, the goal here is to try to make something that is very comfortable for users to use for the whole night sleep. And of course, during sleep, you move, and if you have a hard piece inside your ear, it is really uncomfortable. So the goal now is twofold. One is that we need to make sure that it is comfortable, but at the same time, it needs to maintain a very well contact point between this electrode and the ear, so that it can get out the very good high quality signal. But during sleep, even though the electrode is relatively close to this signal source, it's still very far from those signal sources compared to traditional ways of monitoring these signals. For example, the traditional ways of monitoring EEG is that you attack electrode on top here. And if you attack it there, the distance is much smaller, right? In our case, it's much further. That's why we have to design our electrodes in a way that are different from existing techniques out there. So first of all, we pick the material, which is a viscoelastic foam that has the ability to contract or expand itself depending on the pressure. And as the pressure comes, it will contract. But when there's no longer pressure, it will go back to its original shape. And because of that, it can keep the contact point between the electrode and inside the ear much better. But that's just the first part of the equation, because now the second part is how did you design the electrodes so that it's not only, again, comfortable, but also have high quality. The way we do that is that we first have a thin layer of silver on top. So imagine that you put a thin layer of silver on top of this foam, it will be very, very highly conductive. Great thing. The problem though is, for us to put this earpiece inside your ear, you have to squeeze it and then put it in, so that, and then you wait for it to expand. If you have tried, if you have used viscoelastic foam earplug before, that's what you would experience, right? But if you do that, if you squeeze it, it will fall apart because it's very fragile, right? So that's the problem with the silver material. So what we do is that we have 3-layer design where we first have a pure silver leaf on top, and that attached to a conductive cloth underneath. And in between we use conductive gel that is FDA approved, medically safe, so that it can keep those silver points on top while it attaches down to the conductive cloth. And from that we connect out to the wire and then connect it out to the circuit outside. So the key here is that we have to use a material that is very flexible, and the electrode that must be highly, highly conductive and durable, right? But with this design, now we have a system we can collect signal, and we want to apply this into a sleep study. So this is how the board currently look like, and of course the next step is why we try to minimize this, miniaturize this, and we did an experiment of 38 hours of sleep with 8 different subjects, and with the age of 25, average of 25. This figure show on the x-axis is the segment sequence number for during the whole night sleep, and the y-axis show the quality of sleep going from awake, REM, and 1, 2, and 3. And that is, so so ground truth is show in comparison with the LIBS output. And as you can see here, there are points that is not accurate, but the overall performance is around 95% of accuracy comparing to the gold standard FDA-approved, highly expensive device. The device that we use here is around $48,000, comparing to the device that we made is around $200. It is 3 orders of magnitude cheaper, while we get around 95% of accuracy, right? So that is the application of LIBS with sleep study or sleep quality monitoring. Now, how do we take our platform from here? So, of course, we can use this for in-home sleep monitoring to address the very original problem that I just mentioned about. We want to be able to scan and understand sleep quality for for not only kids but also everyone to hopefully address many of the clinical health problems. But it can be applicable to many other applications as well. For example, seizure detection is one of the potential applications of this system, where we know that in the US we have many traffic accidents caused by a person gets seizure attack when they're driving. And if one great thing about our technology is that we can embed this technology on a earphone. Imagine that you attach this electrode on the earphone, and then using our algorithm, now we can monitor your brain signal, your eye signal, and your muscle signal while you're listening to music, right? So when you're driving, for example, you listen to music, and now I can capture your brain signal. And from that, hopefully we can predict when seizure happen, and from that we can cut down the fatal rate of traffic accidents, or making suggestions to the users. Another potential application is that since we can capture your eye signal very well, and we can capture your brain signal also relatively well, what we can do is that we can tell whether you are distracting from driving, because we can tell where you're looking at. Are you looking forward or you're looking down? If your level of focus is not forward anymore, we can send an alarm, right? Or because now we can monitor your brain signal, we can tell whether you're sleepy or not. So that is, we can do drowsiness detections, or from this we can reduce the driving distractions, which is a huge problem now in the US, right? Another potential application for this is come from medical doctors that come to us after they hear about our technologies, that we can use this to change the way that hearing aids are built now. For example, the current state of the art of hearing aid is your hearing aid would try to zoom in and amplify the sounds coming from the area that create the highest amplitude. The louder it is, the more focused your hearing aid will go into and will amplify. What that means is that if you're going to a bar with a person and you want to talk to that person, and next to you or behind you is a bigger group that trying to that are making a lot of noise, then it's impossible for you to hear what the person in front of you is talking about, right? So, but with our technology, now that we can capture your brain, your eyes, and your muscle signal, we can infer the level of focus that you have, and we can also infer whether you're annoyed or not based on your brain signal, and we can so that the hearing aid can still accordingly, as opposed to just amplify the signal that has highest highest amplitude, right? So we can change the way that today's hearing aids are built. Another application is that since we can capture your muscle signal really well, we can tell whether you're chewing or you're not chewing, how often you're eating, what kind of food you're eating, and from that we can hopefully we can infer even the level of calorie that the person is consuming per day, and we can make suggestions for change the eating habit of people, right? By far the most interested application is evaluating the learnability of kids. So we all know that kids, especially a younger kid, does have hard time of expressing their interest or expressing their the level of engagement. And as a parent, it's very hard for you to also tell whether the kid is like playing game. Well, most of the time the kids like playing game, right? Whether it's the kid like playing piano or violin, among many other subjects. So if we know what the kid likes, then we can orient them. The problem is today's technology doesn't allow you to do that, or it needs to be very clunky, where you need to put a set 16 electrode or 18 electrode or more number of electrodes on the head of a person to infer and to capture their brain signals, so that they can infer the level of attention that the person is having to a certain activity that they have. But using our technology, imagine that you can just put a earplug or earphone to the kid, and then the kid was listening to soothing music when the kid is playing something, and at the same time we can monitor their brain, their eyes, and their muscle signal, and then from that we can infer whether the kids get excited about that subject or not, right? So we can orient the kid accordingly. And of course the wider classification of this system is that we can use this for human-computer interactions, where a person now can control a wheelchair by just thinking about the direction that you're going, or in combination with the eyes movement or the muscle movement. When we combine those different signals, we would allow the user to control, to send input into our computing systems with our LIBS systems, right? So those are the possible applications that the system can realize, and we hope that we would make that happen in the next few years. And what we are going from now is where we're from here is that we try to build a LIBS platform and open source that for the community to build on. And at the same time, we are trying to commercialize this together with a few other technologies that we have developed under medical peripheral groups in our schools that we try to see how can we change, how can we build a new gold standard for sleep study as one, and also opening this platform for the healthcare community to use and to build on. So, and the another direction that we're trying to do is that we have to improve the way that we separate the signal. That's one of the drawbacks of our system now is that we have to do per person training, and of course that doesn't take a lot of time for training, but there's still, it means that we cannot just send a packet to a patient in their house and then they can just plug in and use it, right? They have to actually come to the hospital, we have to hook them up onto our PSG device, which is costly, time consuming. So we are working with a group of researchers to try to generalize and improve the machine learning algorithm so that we can extract the features from general patient as opposed to per person. And we're also trying to miniaturize the hardware and to enable whole night wireless charging through IF beamforming to make sure that we have enough energy for the device to run for the whole night. Right. So with that, that's all I have today, and I would love to take questions.